Hello friends, welcome back to the third lecture of communication system. So in continuation with our second lecture, we have discussed about electromagnetic waves. So here I again repeat the electromagnetic wave. It is a showing a electromagnetic different spectrum of electromagnetic wave. For example, named radio waves, microwaves, infrared, visible, ultraviolet, X-ray, and gamma ray. In the lower scale, scale show wavelength. Similarly, the bottom of the figure show the scale in terms of the frequency. For example, radio waves is the range of 10 to the power 4, microwave in the range of 10 to the power 8. If you are means if you show the waves in terms of frequency. Similarly, if you show the radio waves in terms of wavelength, then it is the range is 10 to the power 3 meters. Similarly, 10 to the power minus 2 meters. 10 to the power minus 5 in the case of infrared. Wavelength in the range of 10 to the power minus 5. Similarly, the frequency in the case of infrared is in the range of 10 to the power 12. So these are the different electromagnetic spectrum. Then again we have summarized with the baseband signal that contain frequency in the audio frequency range. Some form of the band shifting must be employed for radio system to operate satisfactorily. This process is called a modulator. The transmitter block in any communication system contain the modulator device. Receiver block contain the demodulation device. All are we have discussed in the lecture 2. Then a modulator modulates the carrier wave which has a frequency that is selected from appropriate band in the radio spectrum. We have already seen about the radio spectrum, and carrier frequency of the carrier waves is always larger than the frequency of information waves or modulating waves. For example, the frequency of the carrier wave for FM can be chosen from the VHF band of the radio spectrum. AM can be chosen from around a few kilohertz to the few hundred kilohertz. The demodulator extracts the original baseband signal from the received modulator. So the modulation is a process of impressing a low frequency information signal onto higher frequency carrier signal. Modulation is done to bring information signal up to the radio frequency signal. Again, it is the simple basic building block. Already I have explained in the lecture 1. Input there is transducer, then modulator, and then channel, after the demodulation and output device. Then again there are types of the modulation. We have already discussed about amplitude modulation, frequency modulation, and the phase modulation. So the basic in amplitude modulation, there is change in the amplitude. Frequency modulation, change in the frequency, and phase modulation, there is change in the phase. So see this particular diagram. This particular diagram shows the amplitude modulation. First waveform is a carrier wave, second waveform is a baseband signal, and third waveform is a modulated signal. So if we see the third waveform, in the case of the modulated signal, baseband signal is a mirror image. One is shifted to the top, and similarly baseband signal is shifted to the bottom, and between these baseband signal we have draw carrier signal. Just I try to explain how a modulated wave look like. So that is our amplitude modulation. See the circuit diagram of the amplitude modulation. For amplitude modulation, we require an information modulating signal or information signal. Then we use oscillator is used to generate a carrier frequency. We also follow that the carrier frequency is always greater than the modulating signal frequency. After the multiplication, we multiply both the signal, then the output is our modulated signal. See, this particular circuit is a multiplier circuit, and we also use diode as a multiplier. Similarly, if we see the spectrum, Here see the lowest frequency is 530 Hertz, highest frequency is 1700 Hertz, and we have divided the frequency in the interval of 10 kilohertz. It means 530 to 540, 540 to 550, 550 to 560, and that way. And 530 to 540 is basically a band, and the center frequency is 530 plus 5, and 535 is the center frequency in the first case. In the second case, that is represented by the yellow, it start with the 540 and end with the 550, and 545 is the center frequency. In that way we represent. So in the case of the modulating signal, if we see the bandwidth of the modulating signal, it is the 2B, where B is the bandwidth of the modulator. Sorry, if you see the bandwidth of the modulated signal, it is the twice B, where B is the bandwidth of the modulating signal. We explain why the bandwidth in the case of the modulated signal is twice B. Similarly, in the case of the frequency modulation, first is the carrier wave, second is the baseband signal, and third is the modulated signal. So again, the baseband signal, nothing but the information signal. Unfortunately, this graph don't show baseband signal. So if you see the frequency modulated wave, in the case of the frequency modulation, see that in the some portion the wave is compressed, some portion wave is expand. So if we converted this expansion and compression in terms of the frequency, it means if the frequency is high, then the wave will compress, and if the frequency is low, then wave is expanded. So that is in that way we are able to differentiate between AM and FM signal. See that the AM modulated signal and FM modulated signal, you are able to differentiate it. So frequency modulated signal, basically we use a voltage controlled oscillator. We apply the input, and voltage controlled, with the help of the voltage controlled oscillator, we change the frequency of the input signal. Here the bandwidth in case of the frequency modulated signal is infinite in the case of the wide band FM, and if it is a narrow band FM, then its frequency is equal to twice B. So the narrow band FM is nothing but the AM signal, and wide band FM is represented in a different way. And we use the Carson rule to calculate the bandwidth of a frequency modulated signal. The bandwidth of the frequency modulated signal is approximately equal to twice 1 plus B into B, where small b is the modulation index. In the later lectures, we see how to calculate the bandwidth in case of frequency modulated signal. Then our band allocation in the frequency modulated signal, it's vary from 88 to 108 hertz, and one channel bandwidth in the one channel is 200 kilohertz. It means 88 then 288. Then there are no station. The bandwidth of the no station is not shown here, but generally it is not 200 kilohertz, it is less than 200 kilohertz. In that way we allocated the different frequency to different stations. Similarly, the phase modulation, in the phase modulation only the phases of the signal is changed, but it is if you see the phase modulated signal, it's almost look like a frequency modulated signal. Bandwidth in that case is also same, it is equal to twice 1 plus B into B. In the future lectures, we see how to generate a phase modulated signal and how to calculate this particular bandwidth. Then I just try to explain this whole scenario in the particular example. A non-periodic composite signal has a bandwidth 200 kilohertz. Middle frequency is 1 kilohertz and peak amplitude is 20 volt. The two extreme frequency have an amplitude of 0. Draw the frequency domain of the signal. So the lowest frequency is bandwidth is 200 hertz, middle frequency 140. The lowest frequency must be 40 kilohertz and highest frequency is 240. Why? Because the bandwidth is 200 and middle frequency is 140. In that way, if we try to allocate what is the minimum frequency, what is the lowest frequency, what is the highest frequency. So lowest if you choose 40 and highest is 240, then the difference between the 40 and 240 is 200 kilohertz, that is the bandwidth. So at that, in that way we are able to decide the bandwidth. And if we are moving from 40 kilohertz 40 kilohertz to 100 kilohertz, then it has become 140 kilohertz. That is the middle frequency, because the center frequency is always at the middle. It means in the case of the bandwidth is 200 hertz, so the center, if you move left 100 hertz 100 kilohertz and right 100 kilohertz, it means left start with 40, then after 100 kilohertz it is become 140. So 140 kilohertz is given and 200 kilohertz total bandwidth is given. So we are able to identify what is the minimum frequency, what is the maximum frequency. See this, 40 kilohertz, 140 kilohertz and 240 kilohertz. And we have considered the amplitude is a tapered signal. So it start with 40 kilohertz, peak at 140 kilohertz, and again its valley is again around 240 kilohertz. So that is the representation of the. Then in the next example, a non-periodic composite signal is the signal propagated by AM radio station. Previous is FM. Each AM signal station is assigned a 10 kilohertz bandwidth. The total bandwidth dedicated to AM radio range from 530 to 1700 kilohertz. Again, each FM 10 kilohertz. So how another example of non-periodic composite signal is the signal propagated by FM radio station. Each FM radio station is assigned 200 kilohertz bandwidth. So the total bandwidth dedicated to FM signal, again it is the 200. So the middle is 200, then it is 88 to 108. So the difference is around this. Okay. Then we see what is the difference between the AM and FM signal. AM requires simple circuit and very easy to generate. It is simple to tune. It is used in almost all shortwave broadcasting. The area of coverage of AM is greater than FM. It is, but AM is quite inefficient and susceptible to static and other form of electrical noise. This basically we try to summarize all the advantage and disadvantage of AM and FM signal. Similarly, the main advantage of FM is its audio quality and immunity to noise. Most form of static and electrical noise are naturally AM, and an FM receiver will not respond to AM signal. The audio quality of FM signal increases as the frequency deviation increases, which is why FM broadcast stations use such large deviation. The main disadvantage of FM signal is larger bandwidth. So AM is main advantage of AM signal is easy to generate and cover large distance. And main disadvantage of the AM signal is it is quite inefficient. Similarly, main advantage of FM signal is it never is immunity to the noise first, and second is audio quality. Disadvantage of the FM signal is its range is small and its cover larger bandwidth. Then we move the what are the types of amplitude modulation. So first we discuss about the amplitude modulation. So several different way of amplitude modulation of the carrier by MT. First, conventional double side AM, double side suppressed carrier AM, then single side band, and then vestigial side band. each way result in different spectral characteristics and also the different bandwidth for transmission of the signal. Then again I try to explain what is the conventional AM. Then we move under different type of what is the double sideband suppressed carrier AM, what is the vestigial sideband amplitude modulation, what is the single sideband amplitude modulation. So the conventional amplitude modulation is nothing but double sidebands with carriers. So in the case of conventional, we use a adder where empty यानी कि message signal and carrier signal will added. Then we multiply it. It means MT plus AC multiply by cos 2 pi FCT. So that is our output. AC plus MT multiply by cos 2 pi FCT. It is our conventional amplitude modulated signal, and we also see the diagram what is the envelope of conventional AM signal, and I already explained about this envelope. Then that is the again a new diagram. See here, a oscillator where we generate FC. Similarly, we use a modulator that have a audio oscillator. That audio oscillator generate FA, then FC and FA multiply, it's generate AM signal. See here, and that is the basically spectrum of the AM signal. And later slides you know how this particular spectrum is generated. Actually, due to this modulator, FC and FA is multiply, then it's create FC plus FA and FC plus FA and FC minus FA. So the spectrum of FC signal is centered around 0, but spectrum of the modulator signal is centered at FC. So again, if you have the modulated signal, we choose AM cos 2 pi FMT. FM is the modulating signal. Then we have and FM is the modulating signal, FC is the carrier frequency, and FM is the modulated signal frequency. Then the AM signal is AC plus AM cos 2 pi FMT, that is multiplied by cos 2 pi FCT. Actually, in the previous is AC plus MT cos 2 pi FCT. So what is the MT? MT is also a sinusoidal signal. So if MT is the sinusoidal signal, we put MT equal to AM cos 2 pi FMT, where we know the FM, we know the FC. Then our modulated signal is AC plus AM cos 2 pi FMT, and again in the bracket and outside the bracket cos 2 pi FCT. Then after the multiplication, it's become AC 1 plus beta cos 2 pi FMT cos 2 pi this. Then again we multiply. Actually, what we can do a instead of the AM, we write beta. Beta is called the modulation index. So it's become AC cos 2 pi FCT plus beta AC upon 2, and just expand this bracket, we got this. After this, when we got this, we see that modulated signal consists of the frequency FC, FC plus FM and FC minus FM. So FC minus FM is called the lower sideband, FC plus FM is called upper sideband. And if we see that FC plus FM and FC minus FM, so the minimum frequency is FC minus FM, highest frequency is FC plus FM, so the bandwidth is FC plus FM minus FC plus FM. It means that is equal to twice FC. That's why a bandwidth of an amplitude modulated signal is twice of the frequency of the modulating signal. See this here, just show the spectrum. Here each spectrum is shifted around FC. Normally, in case of the modulating signal and modulated signal, spectrum is around the centered around the 0. It means at that point. But due to the modulation, spectrum is shifted at Fc plus Fm and Fc minus Fm. It means it is centered around Fc. So that, and similarly if you see the amplitude, it is A by 1 by 2. See here in the lower side and upper side term, there are term upper side it is the beta AC by 2. It means all the sideband is divided by half. That's why it is here Fc, the amplitude is AC by 2. But in the case of Fc plus Fm and Fc minus Fm, amplitude is AC beta by 4. In the previous slides, we already know how we got AC beta. So that is the basically spectrum. Spectrum is nothing but the frequency domain representation of the signal. In this particular slide, this animated graph actually show the spectrum. Fa, Fc and Fm actually it show the spectrum. Here we choose Fc is the carrier frequency and we choose Fa instead of Fm. In the derivation we choose Fm, but in the pictorial representation we choose Fa. So here that is the power of the carrier component, the power of the sideband component. Then conventional, since the envelope is slowly varying, the positive and negative half of the each cycle have the almost same amplitude. You must careful about this. That is the basically envelope of conventional amplitude modulated signal. Same figure, it is again called a modulated signal. Just at the top and bottom we are not showing information signal. Rest are the same. So here the actually this graph is due to the integral of AC plus mt square cos 4 pi fct. Then similarly in terms of the power, AC square upon 2 plus PM upon 2. Note that the second component is much smaller than the first component, because mod of mt is very small in comparison to the AC. This shows that the conventional AM system are far less power efficient than double sideband suppressed carrier system. Actually, you are saying conventional AM system is consists of the carrier signal and modulated signal. So basically carrier is not of any use, so it is the wastage. So AC square upon 2 is wasted. Actual our modulated signal is consist in the PM by 2. So that's why it is called the less efficient. Even if we suppress AC square upon 2, then our modulating signal become more efficient without any loss, because AC does not consist any type of information. Our information is available in the PM, so we can easily suppress AC square upon 2. It means we are able to save half of the power. That's why we prefer double sideband suppressed carrier instead of double sideband system. Here amplitude, that is the basically again they try to explain what are the amplitude. It had been seen that the top frequency, that is modulated carrier, is 6 GHz. Then the top spectrum will extend to 6 GHz above and below the signal. In other words, the bandwidth occupied by the AM signal is twice the maximum frequency. I already explained. Here what they try to explain, the 6 GHz is the carrier. So upper sideband is start with the 6. It means whatever the upper sideband is showing, its center is 6 GHz. Then 6 GHz is called Fc. So then Fc plus Fm and Fc minus Fm. So if you calculate the bandwidth, it's become twice of Fm. Again there are the same points here. They explain what is the bandwidth, F max upon F min. Then we have write what is the modulating signal. It is AC plus mu cos this. Just here the terminology we use mu in place of the beta, but meaning are the same. Then again you expand it. after the expansion we got AC cos 2 pi FCT is nothing but the carrier signal, and FC plus FM term is nothing but upper sideband, and FC minus FM is lower sideband. It means frequency varies from carrier frequency FC, upper carrier frequency FC plus FM, and lower carrier frequency is FC minus FM. Then F max equal to FC plus FM, and F min equal to FC minus FM. Then if you take the difference of this, if you calculate the bandwidth, it's become twice FM. Then we calculate the power. Then the P equal to Vm upon root 2 divided by 2. That is the reason we are writing AC square upon 2. See this particular AC square by 2 plus Pm by 2. Here see this particular equation. What is P equal to? PT equal to PC plus PUSB plus PLSB. And what is the value of the standard formula of the power is this. Then P equal to PC equal to AC square, AC upon root 2 into square upon R, so AC square upon 2R. Similarly, PUSB equal to AC mu upon 2 root 2, AC mu upon 2, you already know about AC mu upon 2. So that is also equal to 2 root 2, RMS value and peak value and RMS value conversion. Then it become AC square mu square upon 8R. Similarly, we calculate in the case of lower sideband, then the total power is equal to AC square upon 2R, AC square mu square upon 8R, AC square mu square upon 8R. And if you put the mu equal to 1, then it's become AC square upon 2R plus AC square upon 4R. That is the previous expression. But if the modulation index is not 1, then we take the AC square upon 2R common and become 1 plus mu square upon 4 plus mu square upon 4. So if PT equal to PC, 1 plus mu square upon 2. We can use the above formula to calculate the power of the FM wave, AM wave, when the carrier power and the modulation index are known. If the mu equal to 1, then the power of AM wave is equal to 1.5 times of the carrier wave. See from the equation, it is very clear. So the power requirement for transmitting an AM wave is 1.5 times the carrier power for perfect modulation, and basically 1.5, the 1 is the carrier power and mu square upon 2 PC is our modulated power. So this carrier power is useless for me, that's why it is called more inefficient. Then they just, I give you an example, modulating signal MT equal to 10 cos 2 pi into 10 to the power 3 is amplitude modulation with the carrier signal this. Find the modulation index, carrier power and power required for transmitting AM waves. So the MT equal to 10 cos 2 pi into 10 to the power 3t. If we compare with this standard modulated signal, then we got AM equal to 10 volt, FM equal to 10 to the power 3 kilohertz, that is equal to 1 kilohertz. Similarly, equation carrier signal is also given. So after the comparison, we got AC 50 volt and FC 100 kilohertz. Then the modulation index equal to AM upon AC, then it's become 0.2. Then we know what is the formula for carrier power, so we calculate carrier power. Similarly, it means we have carrier power is calculated. Then we know the formula for power required for transmitting, then it is PC 1 plus mu square upon 2. So we calculate our transmitted power. Therefore power required for transmitting AM wave is 1275 watt. Yeah, 1.275 and 1.3 kilowatt. In that way we are able to calculate the formula. So this is the one of the example in which I try to show how to calculate the different value of the different it means different transmitted power, carrier power and so on. And in the next lecture we will again discuss about the modulation index. How do we deal with the mu or beta written here. Thank you.